Hello. In this video we start Unit 7, Polynomial Functions. This is a short unit with only 2 lessons in it. Today we start with Day 1, Identify and Graph Polynomial Functions. In the book we are in section 5.1, and we will cover the first 2 objectives, identify polynomial functions and their degree, and graph polynomial functions using transformations. Incidentally, for Day 2, the second lesson in this unit, we will finish by covering Objective 3. Let's begin. Polynomial functions. Here are some examples of polynomial functions. So take a few seconds, look over these things. What you see is there are a lot of powers of x, and those powers of x are being added or subtracted, and there are numbers in front of those powers of x. The very first one is a very typical example of a polynomial function. 8x to the 10 minus x to the 4 plus 12x cubed plus x plus 17. Incidentally, this minus x to the 4 can be thought of as adding a negative 1 times x to the 4. But those numbers, we call them coefficients, those coefficients don't have to be integers. They can also be more complicated things like pi, or they can be 3.9, that's okay. I don't have to write all my powers descending, like 10, 4, 3, 1, 0. I could write my powers going up, like in my third example with h. And this is a little strange. The p of x, that actually, p of x equals 5, that actually is a polynomial function. Maybe we could think of it as 5 times x to the 0 if you really wanted to. This last one, how about q? Well, I can multiply that out and I get x to the 5th plus 3x to the 4 minus x minus 3. And so there we see more typically the form of a polynomial like you would expect. Here is our official definition. A polynomial function is a function that can be put into the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus on and on, all the way down to a sub 1 times x plus a sub 0, where all of those a's are constants. Can you see what those a values are in the first situation? How about this, f of x? So a sub 10, that's the number in front of x to the 10, so a sub 10 equals 8. And how about the number in front of the 3? A sub 3 equals 12. Oh, and also, by the way, what about a sub 2 in this situation? I don't see any x squared term, so a sub 2 actually equals 0. It's like I have a 0 times x squared, even though you can't see it, 0 times x squared appearing in that polynomial. Some vocabulary. There are a lot of definitions and terms that come along with polynomials, so consider this example function. The coefficients of this function are 8, negative 1, 12, 0, 1, and 17. Those are the numbers that come before the powers of x. There's a negative 1 in here, again because I think of this as 8x to the 5th plus, and then I have a negative 1 multiplying in front of the x to the 4. So that's where that negative 1 comes from. And also, the 0 makes an appearance because I'm thinking that when I get to the x squared term, well, I don't really have an x squared term, so it's like it's being multiplied times 0. The degree of this polynomial is 5. The degree is the highest power of x that appears in the polynomial. The leading term is 8x to the 5th. So once I've identified the highest power, I look at the whole monomial that includes x to that power. In this case, 8x to the 5th. The leading coefficient is 8. That is the coefficient of the leading term of the polynomial. The constant term is 17, so way back at the other side of the polynomial, the thing that doesn't have any x, or maybe you can think of it as 17 times x to the 0, that's my constant term. And lastly, this polynomial is written in standard form, with the powers of x descending. Sometimes you'll see polynomials written with the powers of x ascending, or just kind of jumbled up, but the standard form has it so that the powers of x start high and then go to low. the degree, name, and shape of different polynomials. This gets pretty interesting. You can have a degree 0 polynomial. That's just a constant. That's just a number, and we call it a constant. And the shape of a constant polynomial is just a horizontal line. So how would I graph how would I graph the number 5, right? How do I graph the polynomial 5? It is a horizontal line at height 5. There it is right there. Now, a degree 1 polynomial looks something like this. The highest power of x is 1. And we've seen these before. These are linear functions. When you graph those things out, they just look like lines. A degree 2 polynomial, that's called a quadratic function. And when you graph quadratic functions, what do you get? We just studied these. You get parabolas. They can either open up or they can open down. Degree 3 polynomials are called cubic polynomials, and when you graph a cubic polynomial, you end up getting something that has an extra curve in it. Maybe it's something like this. Degree 4, those are called quartic polynomials, and when you graph quartic polynomials, they get even more complicated. They have yet another turn to them. There we go. Now, they don't always have to have quite as many turns, like this m or this w. You might graph a degree 4 polynomial, and it looks something like this, where it almost, like it wants to be a w, but it doesn't quite dip down. So some of your turns might be straightened out a little bit in your polynomials. One thing that's common to all of these polynomials is that graphs of polynomial functions are smooth, and they are continuous. The domain of a polynomial function is negative infinity to positive infinity. The domain is the set of all real numbers. I can put any real number I want into a polynomial function. Let's talk about the wiggles, the turning points of polynomial functions a little bit more. Here are some typical degree 4 polynomials being graphed. These are all degree 4. Now, some of them turn around. And the points on the graph where they actually change from decreasing to increasing or increasing to decreasing, those points are called turning points. The one that's labeled here has 3 turning points. The one graph on the left, 1, 2, that has 3 turning points also. But let's take a look at the graph on the bottom left. How many turning points does that have? Well, there's definitely one at the very bottom, and this is where the function changes from decreasing to increasing. But as I go to the right, the function is increasing throughout. So in fact, that's the only turning point. There's only one turning point there. Let's look at the graph on the top right. It increases, and then it levels off. And it doesn't quite descend. It levels off for a moment, and then it continues on up. And so that's not a turning point there, but at the very top, I do see a single turning point. So that's okay. So in these graphs, they have either 1 turning point or 3 turning points. Well, in fact, a degree 4 polynomial has at most 3 turning points. It might not necessarily have 3, but at the most, it has 3 turning points. In general, a degree n polynomial has at most n minus 1 turning points. Let's talk about power functions. Power functions are like the simplest kind of polynomial. A power function is just a polynomial that has the form a x to the n. And here are some examples. X to the 5, 3x to the 8, 1/2 x to the 4, negative 5x cubed, negative x to the 7. Let's see a demonstration with some different power functions. Here we go. Right here we see x squared. This is the function x squared. I've got it labeled up to the left. And I can change the degree of this. Instead of x squared, I can make this x cubed, x to the 4, x to the 5, x to the 6, x to the 7, x to the 8. And you see the pattern at this point, how it goes on. One thing I wanted to emphasize is how it becomes flatter against the x-axis, close to the origin. Let's see that again, and look how it squeezes in. Oh, I could do also x to the 1. There we go. This is just the function f of x equals x. And as I increase the degree, it will get flatter. It'll get squeezed in more against the x-axis. Here we go. X squared, x cubed, x to the 4th, x to the 5th, x to the 6th, x to the 7, x to the 8. So that's something to notice. It becomes flatter. It also gets sort of stretched up more, it becomes a little skinnier. Um, Also, all of these functions pass through 1, 1. Why should that be? Well, if I plug 1 into x to the 8, what do I get? Well, 1 to the 8 equals 1. If I take this down to 7, 1 to the 7th power is 1. 1 to the 6th power is 1, right? And so all of these functions pass through 1, 1. And of course, they also pass through 0, 0, because 0 raised to any power is 0 again. So that's kind of interesting. I have these 2 points that always stay in my power functions. Also, it flips back and forth, right? When it's an odd power, like 3, the 2 branches of the function, one goes down and one goes up. And this because with an odd power, when I take a negative x value and I raise it to an odd power, I get a negative x value again. If I put, for example, negative 2 into x cubed, negative 2 times negative 2 times negative 2, that's negative 8. So although we don't see it on the graph, well, here we go. If I plug in negative 2 into my function, the y value that comes out is a negative 8. The last thing I'll address is the coefficient in front. This is 3x squared, and by changing this point I can make it skinnier, and so an x squared function that's skinny, sort of stretched vertically, has a big coefficient, but if I make it nice and wide, then that coefficient is very small. And the same thing goes for all of these other powers as well. Let's try x to the 6. And it's already pretty skinny to begin with, but if I stretch it up vertically, it gets even skinnier, and you can see that the coefficient in front of that is bigger than 1. But if I make that coefficient less than 1, very small, 1 over 4096 times x to the 6th, I get a very wide function. And then negatives as well. Let's say x to the 6, but then I bring it down. Here's my function negative x to the 6. Here's negative x to the 5. Negative x to the 4. Negative x cubed. Negative x squared. So it's just like all the positive versions that we saw before, except flipped vertically. Let's return to the slides. The end behavior of power functions. So what happens with these different power functions as x becomes really, really big or really, really small, like in the negative direction? This is what we refer to as the end behavior. Now, if our n is even and I have a positive coefficient, then we get functions that look like this. These are the graphs of x squared, that's in orange, x to the 4, that's the one in blue, and x to the 6, that's the one in green. So as my even power increases, it gets skinnier and it becomes tighter down against the x-axis. But what about positive coefficient with n being odd? Do you remember those? So the 3 functions graphed here are x cubed, x to the 5th, and x to the 7th. They all kind of have a very similar shape. Now, what about if I have negative coefficients? Again, with n being even, so negative x squared, negative x to the 4, negative x to the 6, those look like the U shape, but now flipped over. So negative x squared is the orange, negative x to the 4 is blue, negative x to the 6 in green. Negative coefficients with n odd, it's like the picture above, but just flipped vertically. And these are the functions negative x cubed, negative x to the 5th, and negative x to the 7. Transformations of power functions. Can you see this? What does the graph of x minus 2 to the 5th plus 3 look like? We've seen something very similar to this with quadratic functions, but now I have a 5th degree function. Intuitively, it feels like we probably want to start with the function x to the 5. X to the 5, what does that look like? Very roughly, something like that. Then, following what we did with quadratic functions, this minus 2 on the inside means I'm shifting 2 units to the right. And the plus 3 on the outside means I'm shifting 3 units up. So let's take this graph of x to the 5. We'll move it 2 units to the right and 3 units up. So very roughly, I go 2 to the right, 3 up. I place the point there. And this graph has shifted up to that point. So maybe something like that. What point used to be at the origin is now at 2, 3. Let's see how that compares to the real graph. Let's make the graph of x to the 5. And then I will translate it 2 to the right. So I have x minus 2 to the 5th. And then I'll move it 3 units up. 1, 2, 3. And there we go. So that is really what the function x minus 2 to the 5th plus 3 looks like. How about the next one? What does the graph of 2 minus x plus 3 to the 4th look like? This one has a little bit of a trick to it. Do you see what the trick is? Maybe I could write this as negative x plus 3 to the 4th plus 2. And I have something being raised to the 4th power, so maybe I want to begin by thinking about x to the 4th. What does x to the 4th look like? It looks like kind of like a parabola, but squeezed in down against the x-axis a little bit more. So there's my x to the 4. But I don't want x to the 4. How about negative x to the 4? Negative x to the 4 looks like that parabola again just flipped over. But now I can translate negative x to the 4. Now the plus 3 on the inside means I want to shift it left by 3, and the plus 2 means shift up 2. All right, so I'm going to take this picture of negative x to the 4. I'll shift it left 3 and up 2. So I think I'll get a graph that looks something like this. Let's see if that's right. So I'll come back. Let's make negative x to the 4. There's a negative. Okay, so there's where I'm starting, negative x to the 4. Shift left by 3. That puts the plus 3 on the inside. Shift up 2. And that gives me the plus 2 on the outside. And there it is. There's the function I was looking for. Well, originally it was 2 minus x plus 3 to the 4th, but same thing. Last topic is the end behavior of polynomials. We talked about the end behavior of power functions, like does the function go down to infinity or up to infinity? Does it go up on both sides? But now let's think about polynomials in general. What is the end behavior of this guy, x to the 4 minus 2x cubed plus 2x? If I make x get really, really big, does this value get really, really big or really, really low negative? And if I make my x get really low negative, what is f of x? Does it increase higher and higher, or does it get lower and lower? Here's the picture. This is the graph of f of x. So it turns out that as my x gets bigger and bigger, those y values, those function values, get larger and larger also. So this is how I fill in the first blank. As x increases to infinity, f of x, that's the y values, f of x also increases to infinity. Now what about as x goes to negative infinity? So now I'm thinking in this direction. X gets lower and lower and lower to negative values. Well, those y values, what does the function do? It's going up and up and up. So as my x goes down to negative infinity, my y values, my function values, are increasing. So as x goes to negative infinity, f of x goes to positive infinity. Now, how could I have done that without the graph? That's really what we want to figure out. And here's the trick. To determine the end behavior of a polynomial, examine the leading term. In this example we just did, the leading term was x to the 4. And what does x to the 4 look like? X to the 4 is roughly like a parabola that's squeezed down a little bit. And look, its end behavior is the same thing. As x goes to infinity, f of x increases to infinity. As x goes to negative infinity, f of x goes up to positive infinity. It turns out that the end behavior of that leading term is the same as the end behavior of the polynomial as a whole. It's because with the highest power, when x gets bigger and bigger and bigger, this highest power of x will overpower everything else. The function looks more and more just like x to the 4. It's kind of a funny thing. And also as x gets lower and lower negative, then the function as a whole starts to look like the leading term because that has the highest power. It starts overpowering everything else. Let's do an example where we don't graph the polynomial. Here we go. What is the end behavior of this guy? F of x equals negative 3x to the 7 minus 12x to the 6 plus 2x cubed minus 44. Do you see the answer? Can you think about this? Pause the video if you'd like. All right, so here's what we do. We look at the leading term. The leading term is negative 3x to the 7. What does that look like? Well, I first think about x to the 7. X to the 7 looks like that. And 3x to the 7, we'll just sort of expand it up, we'll stretch it vertically. Negative x to the 7 will flip that over, like that. And so negative 3x to the 7 just stretches that vertically. I don't even know you can really see any real difference there, but pretty much the same. And so this is the kind of thing that we're looking at. And I can recognize what this end behavior is. As x goes to positive infinity, my function values are decreasing. So that goes to negative infinity. And as x goes to negative infinity, those function values are increasing. So as x goes to negative infinity, f of x goes to positive infinity. All right. This is a good place to wrap things up. We've talked about a lot. Polynomials are interesting. They're shapes. They can take all different kinds of shapes, but the degree plays a big role in what the shape of the polynomial looks like. And also that leading term is really important to telling us how the end behavior works out. So a lot of things to appreciate about polynomials. All right, this is a good place to stop.